HVAC Chiller Plant Optimization, Case Study. Welcome to the HVAC Chiller Plant Optimization module. In this session, we'll delve into the key challenges and solutions associated with optimizing chiller plant performance. From addressing low delta T syndrome to ensuring efficient auxiliary pump operation and maintaining high-quality condenser water, this case study will provide practical insights and strategies to enhance energy efficiency and system reliability. We're exploring a critical topic in HVAC systems: optimizing chiller plant performance. Our focus is on tackling issues that can drive up energy costs and impact system efficiency. Let's start with low delta T syndrome. This is a common issue that occurs when the air handling units have temperature setpoints below their designed range. Let's explore the low delta T syndrome, which can present a real challenge, especially in large capacity chiller plants using primary-secondary pumping systems. But what does low delta T really mean? Essentially, it's when the chilled water temperature difference, or delta T, isn't maintained as planned. This condition leads to a higher temperature of the chilled water returning from buildings, which then mixes with new chilled water, raising the overall supply temperature. Now, let's discuss the performance of chiller heat exchangers. For optimal chiller performance, maintaining a small temperature difference, ideally around 2.2 degrees Celsius, is key. When this difference gets too high, it impacts efficiency. Several issues can contribute to this, such as fouling in the tubes, inadequate water flow, or a shortage of refrigerant gas. If a chiller's tubes get fouled or blocked, heat transfer slows down, forcing the chiller to consume more energy to keep temperatures low. So, maintaining clean tubes and proper refrigerant flow isn't just for efficiency, it's also for longevity. Let's discuss the impact of high condenser water temperature, which can significantly affect chiller performance and efficiency. If the condenser water entering the chiller is too warm, the chiller has to work harder to reject heat. This typically results from poor cooling tower maintenance or incorrect sizing of cooling towers. Imagine a cooling tower that's too small or clogged with debris. Condensed water flows in warmer than it should, increasing the load on the chiller. This leads to a cycle of inefficiency, driving up energy costs. Let's highlight the importance of properly sizing chiller auxiliary water pumps, as incorrect sizing can lead to performance issues. If these pumps are oversized, they deliver a higher flow rate than the chiller needs, leading to throttling within the chiller itself. This causes an increase in pressure and energy consumption. The solution lies in careful calculations, selecting pumps that operate at their best efficiency point. Imagine designing a pump that fits perfectly into a chiller system without overburdening it. This reduces energy waste and prolongs equipment life. Let's emphasize the importance of condenser water quality, as maintaining high quality is essential for efficient chiller system performance. Low quality water can introduce scale, metal corrosion, and biological fouling. Each of these issues reduces heat transfer efficiency, leading to higher operational costs and potential system failures. Think of a scale layer forming on the chiller's internal surfaces, like wearing a thick jacket on a hot day. Heat can't escape easily, so the chiller consumes more energy to compensate. Let's address the issue of inaccurate sensors in HVAC systems, which can lead to hidden costs and unnecessary energy consumption. Studies show that a mere 1 degree Celsius decrease in chilled water temperature can raise energy consumption by 1% to 3%. Faulty temperature and pressure sensors, along with water flow meters, can give incorrect readings that make the system work harder than needed. Imagine setting your thermostat to a comfortable level, but your thermometer misreads it by 2 degrees, making your AC run constantly. Calibration is key here. Ensuring sensors provide accurate data can lead to better system control and energy savings. Let's consider the performance comparison table, which helps assess chiller performance by comparing chiller panel readings with calibrated instruments. By examining metrics like water temperature, flow rates, and pressure drops, we can spot discrepancies and make adjustments. Calibration isn't just about accuracy, it's about understanding the system's true performance and making informed decisions. Imagine adjusting your system based on accurate readings. It ensures the chiller runs at peak efficiency, reducing both costs and carbon footprint. In conclusion, HVAC systems, especially air conditioning, consume around 40% to 50% of a hotel's total energy. This underscores the importance of efficient chiller operation to reduce energy use and prevent equipment degradation. Challenges such as incorrect temperature differences, low-quality water, and inaccurate sensors add up, affecting system performance and operating costs. But, with technologies like building management systems and IoT, we have ways to address these challenges. These technologies allow us to monitor, adjust, and optimize energy consumption, achieving savings of up to 30% to 50%. Imagine a future where all these issues are detected and resolved automatically. These technological solutions hold the potential to revolutionize HVAC efficiency. Thank you for your attention throughout this HVAC chiller plant optimization module. We appreciate your commitment to learning about optimizing chiller plant performance and addressing common challenges in HVAC systems. In the next session, we are going to learn about HVAC control systems.